speaker is Amudhan Krishnaswamy Usha from Texas A&M University. He is going to talk about spectral operators in finite von Neumann algebras. Over to Amudhan, please.
Many thanks to the organizers for giving me an opportunity to speak. Okay, so I only have 10 minutes, so I'm going to make this quick. Okay. So, is the whole slide visible to everyone? Okay. So,
yes.
Basic notation which I'm going to follow is that H is going to denote Hilbert space. B of H is going to denote bounded operators on H. So these are bounded continuous linear operators on H. And by the spectrum, I mean the usual thing, which is that the set of scalars, so that lambda minus t is not invertible it doesn't have a bounded inverse, in other words. And for me, projection, by a projection, I mean self-adjoint bounded operator, which whose square is itself. So p square is equal to p. And an idempotent is just, without the self-adjoint condition, it's just going to be q square equal to q. So the difference is for projection, the range and the kernel are orthogonal to each other. This is not true for the not necessarily true for the idempotent. Okay, so start with something which is well known in functional analysis, which is the spectral theorem for normal operators. And one version, there are many versions. One version says that if an operator is normal, then there exists a projection valued spectral measure such that you can recover the operator by some sort of integral with respect to this projection valued measure. So what do I mean by a projection valued measure? So this is a map which sends a Borel set to a projection so that the whole space gets sent to one. So by one here, I mean the identity in my space. So in my space would be, so this is the identity operator, in other words. And the intersection is given by the product of these two things, these two projections. So in particular, these two projections commute with each other. And finally, you have this countable additivity like you would have for a measure. So the projection corresponding to the union is given by the sum, and this sum converges in pointwise. So this is in the strong operator topology. Okay, we can weaken this a little bit and ask for an idempotent valued spectral measure. So instead of having these things be projections, you have them be idempotent. So you remove the self-adjoint condition, and everything else is the same. We do have to add one more condition, which is you want the supremum of these norms to be finite. And this is necessary because the norm of every projection is just going to be one, but this is not true for idempotence. So Dunford was back in the 1960s. He generalized this, and he said an operator is he called it a spectral operator if there exists an idempotent valued spectral measure, so that first off, EB T is T times EB. So in other words, these idempotents commute with the operator, which in particular implies that the range of these idempotents is an invariant subspace for T. And secondly, that it behaves well with respect to the spectrum. So if you restrict it, if you compute the spectrum, when you restrict it to the range, that is contained inside B closure. So there's this nice, if it has these nice spectral properties, then such an operator is called a spectral operator. And it's called an operator of scalar type if all of this is holds, and you can like in the case of a normal operator, you can recover it by this sort of integral. I'm not going to talk about what I mean by this integral, but this is very straightforward. You basically take, you ask for the convergence in the strong operator topology, and you do this sort of, say, Riemann sum, and that should work. Okay. So Dunford characterized these operators, said something is a scalar type operator, so it has these sort of this spectral measure, idempotent valued spectral measure, if and only if it is similar to a normal operator. And moreover, this thing that the similarity comes from the bicommutant of S. That's a side note. It's not okay. So, and he also characterized this as it's a spectral operator if and only if it is similar to the sum of a commuting normal operator and a quasi-nilpotent operator. So this is the analog of the Jordan canonical form for matrices in one sense, because what the Jordan canonical form says is you have this sort of diagonal plus this off diagonal, and these two things commute with each other. So every matrix is similar to something of that form. It's similar to a normal matrix plus a nilpotent matrix, both of which commute with each other. Okay, we can weaken spectrality a little bit, and this was done by Foish. These are called decomposable operators. So you say it's decomposable if it has a spectral capacity, and okay, so a spectral capacity is, the details are not relevant for us right now, but basically you weaken it a little bit by, instead of asking for odd Borel sets, you ask for closed sets, and you weaken it instead of asking for unions over infinite unions, you ask for finite unions for just open covers and so on. So this is clearly a weakening, and so spectral operators are decomposable with and the capacity corresponds to the spectral measure in this way. So, okay, I'm going to shift gears a little. So what we were working on is a finite one-dimensional algebra. So this is a star subalgebra. It's closed under the strong or weak operator topology, and there's a nice trace. By nice, what I mean by a trace is it's a linear function which has this so-called trace property, and it takes the identity. The trace of the identity is normalized to 1. The trace of a positive element is positive, and it has reasonable continuity properties, which are not relevant to the point. But so these are finite non-M algebras. So if you have this tool, this of a trace, you can in fact convert these projection valued measures for a normal operator into actual measures on like a probability measures. You take a trace, you take the trace of these projections, and this gives you a measure. What Brown did in '83 is he showed that you can in fact do this not just for normal operators, you can find something similar for any operator in a finite one-dimensional algebra. So there's some sort of good probability measure, and it's constructed by this way. It's again, you take the Laplacian of the log of the determinant of t. So the trace of the log is what's the determinant. So and this Brown spectral measure is supported inside the spectrum, but the support can be much smaller. And just as in the case for the normal operators, this Brown measure in fact arises out of a projection, out of projections, and which are constructed by Hagerup and Schultz. So for any Borel set, you have unique projections, so that it's an invariant projection, and the trace of that projection gives you the Brown measure of that Borel set. And if you restrict your operator to that appropriate subspace, the Brown measure is also going to be supported inside B, and this is the maximal projection, so that this happens. And in general, this is not a projection valued measure, since these projections need not commute. Okay. And they also showed that the projection is the Brown measure is supported exactly as delta 0. So it's the delta measure on 0, if and only if this limit is 0 in the strong operator topology. And this is exactly similar to what happens for quasi-nilpotent operators, where the spectrum is 0. So this is if this object, this norm converges to 0. So you call these SOT quasi-nilpotent operators if it's supported at 0. Okay. So what we show is that if these operators have what's called the uniformly non-zero angle property, that is, if the angle between these Hargroup-Schultz subspaces, if you compute the angle between the subspace, the projection corresponding to B and the projection corresponding to B complement, if this angle is uniformly bounded away from 0, then you can construct lots of good idempotents because of basic linear algebra. Okay, I'm going to skip ahead. You can construct lots of idempotents, and what happens is these idempotents behave well. These idempotents, in fact, give you the idempotent valued spectral measure. So you have this similar characterization, that is, the following are equivalent, that is, an operator has the UNZA property, the uniformly non-zero angle property, that is equivalent to the fact that it can be expressed as the sum of a commuting normal operator and an SOT quasi-nilpotent operator rather than a quasi-nilpotent operator. So it's similar to this. And if you impose the additional condition of decomposability, decomposability forces the converts SOT quasi-nilpotent operators into quasi-nilpotent operators, because the support of the Brown measure is, in fact, the spectrum. And if you do that, you have the corollary, which is a complete characterization of spectral operators. That is, it's spectral if and only if it is decomposable and it satisfies the UNZA property. Okay, I will stop here because I think that is my time. But I just want to note one final thing, which is we can use this. In fact, this is nice. Like off itself, I think this is nice, but we use this to show that classical operators from free probability are not spectral. So in particular, the so-called circular operator, which comes out of, which is the non-commutative analog of the complex Gaussian. This operator, the Z, we show is not spectral. Okay, sorry for, I think I went over a few minutes. I will stop here. Thank you.
We have 2 minutes. If anyone has any question, please go and ask. Okay, if there is no question, let's thank the speaker.